The Earth is our home. Our natural environment results from complex relations between the sun, the oceans, and the atmosphere. The polar ice and the tropical heat represent the extremes of our planet's climate. In reality, this is a very narrow temperature band, completely different from any other planet we've observed. The stability of the Earth's environment has allowed life to emerge, and life has changed the planet. As far as we know, the Earth is the only planet in the universe to have given rise to life. The Orion Nebula is a vast cloud of gas and dust in the Orion constellation. It's a place where new stars are being created. As part of the nebula condenses, it separates into clumps. As each clump contracts under its own gravitation, it begins to swirl, flattening into a disk. They're called protoplanetary disks, or proplyds. In the center of a proplyd, as the molecules are squeezed together, a fusion reaction begins and a star ignites. Some proplyds, occurring close to an established star, shine brightly under the influence of their neighbor. While this makes them easier to observe, the glowing gas and dust is being stripped away by the stellar winds from the adjacent star. Dark proplyds, only observable as silhouettes, maintain their surrounding ring of gas and dust. As the system matures, this stellar debris will form a planetary system. The Hubble Space Telescope has recorded numerous examples of this process, enough for astronomers to understand that the formation of planets is commonplace. This is how our own sun started its life 4.6 billion years ago. But the planets would take longer to emerge. Small grains within the disk began accreting, forming planetesimals. The larger a clump became, the stronger its gravitational attraction, in turn leading to more rapid growth. An early version of Jupiter would have been the first to coalesce, completely clearing its orbit. Around a core of heavy metal and rock, Jupiter's atmosphere, mainly of hydrogen, was compressed by its strong gravitation. Any solid surface lay beneath thousands of kilometers of liquid gas. Our observations of exoplanets have revealed Jupiter-sized gas giants orbiting close to their stars. Astronomers believe the young Jupiter would have begun a track toward the Sun, dragging asteroids and comets in with it. But Jupiter's inward path reversed as it was pushed into an orbital resonance with the emerging Saturn. Not all of the objects forming in the early solar system stayed orbiting the Sun. Smaller objects passing a planet would be deflected by the stronger gravitation, or even captured, becoming a moon. It is thought that there were up to 20 smaller planets orbiting in the inner solar system, from which the 4 remaining terrestrial planets were formed. At this time, collisions in the developing planetary system were common, and evidence from the Apollo moon rocks suggest an impact between the early Earth and an ancestor of our moon was important in our planet's evolution. The Earth has a larger than expected iron core, and gravitational analysis of the moon suggests its core is lighter than expected. A collision between the bodies would explain the moon's loss of much of its heavy material to the more massive Earth. The impact was a glancing blow that set the Earth rapidly spinning with a 5-hour day. The Moon that we know coalesced from the molten debris. Although our Moon is not the largest in the solar system, it is closer in mass to its parent planet than any other moon. The stabilizing effect that the Moon has upon the Earth's rotation is significant. Over long periods, the Earth's axis will vary by as much as 1 degree. Without the Moon's influence, this variation could be as much as 85 degrees, with drastic implications for the climate's stability. The debris in the early solar system was cleared by the planets in a period called the Heavy Bombardment. The emerging Earth was peppered with asteroids and comets, delivering water necessary for life. While tectonic forces erased the bombardment scars from Earth, the Moon, which endured the same travails, is still covered with craters. When chaos in the developing solar system settled down, the young Earth was in a unique position. The Earth's distance from the Sun was just right for the abundance of water on the planet to exist in liquid form. As the Moon had drifted away, the planet's rapid rotation had slowed, and the Sun's heat was evenly shared across the surface. The Earth's large metallic core, combined with the planet's rotation, meant that a magnetic field stretched out around the planet, deflecting the charged solar wind and protecting the surface from extremes of solar radiation. In a hostile universe, the Earth was a uniquely benign environment. The geological record shows that around 2.7 billion years ago, oxygen began occurring in the atmosphere. The vast iron ore regions of Western Australia were formed as iron in the oceans reacted with the new abundance of oxygen to form iron oxide. Simple plant life was using the sunlight and carbon dioxide to live, and it produced highly reactive oxygen as a waste product. This enabled more complex life to emerge, building an intricate web of interrelated plants and animals, completely transforming the planet. The change in the atmosphere had other dramatic consequences. Oxygen stripped much of the highly insulating gases from the air, drastically cooling the Earth. A sequence of ice ages began. Though there is an abundance of evidence showing planetary glaciation punctuated by warm periods, the factors triggering these cycles are complex. Fault lines are clues to the movement of continents, leading to diversions of ocean currents. The effect of volcanic activity on the atmosphere. And changes in the direction of the Earth's axis with regard to our planet's elliptical orbit around the Sun, all contributors to long-term fluctuations in the Earth's climate. Analysis of ice cores deposited in the Antarctic or Greenland is an accurate way to see how the composition of the atmosphere has changed over the previous 800,000 years. Bubbles of air caught between snowflakes before being rigidly trapped as the snow becomes ice can be accurately sampled. One thing is clear: carbon dioxide reaches a peak of around 270 parts per million during the warm periods and drops to approximately 170 parts per million when glaciation is at its greatest. But from this data, it's hard to know if extra CO2 causes the warming or the warming leads to extra CO2. In 1958, Dave Keeling, working for the Scripps Institute, began recording accurate levels of atmospheric CO2 at the Mauna Loa Observatory in Hawaii. It was the beginning of a unique record known as the Keeling curves. Keeling's graph revealed a seasonal variation corresponding to spring and summer in the Northern Hemisphere, where landmass and plant cover is greater. During the northern spring and into the summer, CO2 levels dropped because of the increase in photosynthesis. by the 1970s, a disturbing trend had emerged. CO2 levels were in a steady rise. At first, there was uncertainty about the implications. Extra CO2 could trap more heat, leading to a warming effect, known as the greenhouse effect. But some scientists were worried that aerosol pollution could attenuate levels of sunlight reaching the planet, resulting in a cooling environment. As the decades passed, different pieces of evidence were collected. Drill cores from the ocean floor revealed that ice ages had been triggered by Milankovitch cycles, the variations between Earth's tilt and its elliptical orbit. Though these effects were minor, the correlation was obvious. If such a small nudge could alter the climate, perhaps changes in CO2 could as well. Scientists were realizing just how poorly they understood planet Earth.
A Thor Delta rocket blasts aloft from Cape Canaveral, carrying a robot weatherman into orbit for America's...
At the beginning of the space age, scientists were keen to make weather observations from orbit. Launched in 1960, Tyros-1 was the first weather satellite. It was equipped with 2 TV cameras, regularly transmitting images of global cloud patterns. It provided meteorologists with a unique view, and it was followed by improved versions. Because these early satellites were in highly inclined low Earth orbits, the data gathered covered the whole planet, and it was shared across the world. Since 1873, nations had been cooperating on weather prediction via the International Meteorological Organization, which in 1951 became the World Meteorological Organization, an arm of the United Nations headquartered in Geneva. With a UN resolution calling for international cooperation in the peaceful uses of outer space, weather satellites of different nations were soon being coordinated for the benefit of all mankind. In 1964, the Nimbus program began. The series of 7 satellites included a more sophisticated set of sensors. Nimbus was a testbed for new technologies, and it gathered data about different areas. Along with cloud patterns was information about the atmosphere and sea ice. This was the pre-digital age, and all electronic image data was burnt to and stored on 70mm film. Little thought was given to establishing an archive for future reference. The Nimbus program was an early example of Earth observation rather than just a group of weather satellites. And meteorologists started seeing the planet as a complex and interconnected system. Today, a fleet of satellites is in operation, monitoring the atmosphere, the oceans, the ice, the land, and the biosphere. It is now understood that ice, particularly sea ice, plays an important role in the Earth's climate system. Polar ice slowly flows to the coasts where it melts, providing a source of cold water that drives the ocean currents responsible for the transfer of heat from the equatorial regions to the poles. These currents also move nutrition, which is important for the survival of life. Global winds also circulate water via clouds, keeping the land moist and able to support vegetation. Plant life in both the oceans and the atmosphere removes CO2 from the air and replenishes the atmospheric oxygen. Both the ice, known as the cryosphere, and the clouds reflect a proportion of the sun's energy back out into space. The extent of the ice and cloud cover are important factors in the Earth's energy budget. As ice melts, it exposes ocean or rock, which absorbs more solar energy. Similarly, cloud cover, or the absence of it, will have an effect upon the land or sea beneath. Vegetation is also an important climate factor, as land plants pump huge amounts of water vapor into the atmosphere. But things are changing. Humanity, simply through weight of numbers, is influencing key elements of the planet's climate system. In 50 years, the Earth's human population has risen from just over 3.5 billion to 7.7 billion today. More people need more resources. And while there have been revolutions in agriculture and in technology, the Earth's reserves are not limitless. In 1979, Europe began launching spacecraft. And while the new Earth observation satellites were revealing changes, scientists were reluctant to reach conclusions about long-term trends. They understood that there was a certain amount of variability in the planet's climate cycle. And though climate science knew about the steady rise in atmospheric CO2 revealed by the Keeling curve, researchers were looking for additional, solid evidence that change caused by human activity was happening. Since 1913, spectroscopy had revealed that a layer of ozone in the stratosphere blocked harmful UV sunlight from reaching the ground. In 1974, Mario Molina, a postdoctoral fellow working on hot atom chemistry, published a paper suggesting that the family of industrial chemicals known as chlorofluorocarbons, or CFCs, could damage the ozone layer. In the 1980s, meteorologists working in Antarctica found the evidence. The polar vortex above the southern continent concentrates the CFCs in the stratosphere. Mother-of-pearl clouds in the polar skies contain ice crystals which, in combination with ultraviolet, split chlorine from the CFC molecule. Each chlorine atom can break down over 100,000 ozone molecules. A large area centered over Antarctica showed almost no ozone. It became known as the hole in the ozone layer. The United Nations began talks aimed at limiting the production of CFCs, and in 1989, an international treaty, known as the Montreal Protocol, capped the production of CFCs and ultimately resulted in a 10-year phase-out of CFC production. All countries signed the agreement, and the Montreal Protocol is seen as a model of international cooperation. In the 1980s, an upward trend in global temperature averages was becoming clear, and a scientific consensus emerged that the burning of fossil fuels was altering the balance of gases in the atmosphere. Most of our planet's fresh water is locked in the polar ice caps. 61% of this ice covers the Antarctic continent. In the north, Greenland is also covered by an ice sheet. There is no landmass at the North Pole, but a large area of sea ice grows and shrinks with the seasons. Seasonal sea ice also fringes Greenland and Antarctica. Ice shelves are a third manifestation of polar ice. These are thick layers of ice that extend into the ocean from the mouths of glaciers. Periodically, icebergs will break away from these regions. These areas are important to the circulation of global winds and ocean currents. And since 2002, NASA has tracked the prevalence of water in general and ice in particular via the GRACE satellites, which were recently replaced by a similar pair of GRACE follow-on satellites. The two follow the same orbit, and minute changes in the Earth's gravitational field will cause them to change speed, with a variation in the distance between them. This data is accurately measured, allowing researchers to record changes due to variations in groundwater or in ice thickness. During the life of the first GRACE mission, Greenland lost 285 gigatons of ice per year. On average, Antarctica lost 137 gigatons per year. From 2005 to 2016, sea levels rose by 3.7 centimeters due to melting ice sheets and to expansion of seawater. Sea levels have been monitored from space since 1992, initially with the TOPEX Poseidon satellite, and more recently with the JASON series of satellites. JASON 3 uses a precision radar altimeter to measure regional and global variation in sea levels. In the 20 years to 2014, the average rise was 6 centimeters, but the increase is not uniform. The red areas show the greatest rise, with white representing no change, and blue signifying a decrease. The unevenness of the sea surface is due to a complex interaction between ocean currents, the Earth's spin, and the topography of the ocean floor. All these factors must be accounted for to arrive at a baseline against which to measure changes. These blue areas in the Atlantic show a shift in the Gulf Stream. The Camargue region of southern France is a low-lying area at the delta of the Rhône River. In the 1980s, a seawall was built to prevent the encroaching Mediterranean. Over the last 30 years, the coastline here has been pushed back by several hundred meters. Scientists are convinced that a warming global climate is responsible, and that our reliance on the burning of fossil fuels has led to an excess of carbon dioxide in the atmosphere, which traps heat. 93% of this heat has been taken up by the oceans. Data from the Argo network of ocean buoys shows an average warming of 0.9 of a degree Celsius since the 1950s. While this may not sound like much, meteorologists understand how sea surface temperatures drive hurricanes and cyclones, and early predictions of storms of greater magnitude are being realized. Long-standing weather records are being broken and broken again. In 2017, NASA, NOAA, and the UK Met Office all agreed that 2016 had been the hottest year on record. Globally, 16 of the 17 hottest years have all occurred since the year 2000. Both NASA and ESA have been monitoring the distribution and concentrations of CO2 in the atmosphere since 1992. This visualization from data collected in 2006 shows the yearly fluctuations of carbon dioxide and carbon monoxide. While most CO2 emanates from the populous northern hemisphere, seasonal fires in Africa, Australia, and South America generate much of the carbon monoxide. Prolonged droughts and more severe forest fires are another aspect accompanying increased levels of atmospheric CO2 that are currently unfolding. Such events inject a huge pulse of greenhouse gases into the atmosphere, magnifying the problem. The European Space Agency's Copernicus program, with its Sentinel Earth observation satellites, has committed to making information about the changing climate freely available to policymakers, businesses, and research institutions. Josef Aschbacher is ESA's Director of Earth Observation Programs.
What you see here on this graph is the CO2 concentrations of the atmosphere over the last 800,000 years. And you see that these values are going up and down in different phases. You see on the blue lines here are indicating ice ages, and the orange lines here are indicating periods between ice ages or periods where it's much warmer. But you also see that over the last 800,000 years, the value was always below 300 parts per million, and suddenly, since the last century, it goes up very steep towards 400 parts per million or even beyond.
Distinguished delegates,
the recent climate summit, COP25, held in Madrid, made little progress toward an international agreement to cut greenhouse gas emissions. While some businesses and economies will have to adjust, that task only gets more difficult as time passes, and far greater adjustments will be forced upon everyone. The Earth is the only place we know that harbors life, but the stability that has enabled this web of life is fragile. Plants and animals interact for mutual benefit. Our benign environment results from the complex and varied creatures with which we share the planet. It's important that we look after our home.